Okay, great. Thank you for this opportunity. I'm one of those academics that after 25 years in the US, I decided to move to Europe. So if you want perspectives about both sides of the Atlantic, we can talk afterwards. So I will present a summary of a paper that will come up at ICML this summer with these two brilliant students. It's all about data selection and data pruning. So of course, you know about neural scaling laws. These models are very data hungry, and unfortunately, the test loss only drops as a power law with a very small exponent of the data set size. What Jay was talking about, you know, these huge data sets that are required. And this raises the question, can we basically learn in a more data efficient way where we throw away the data that are not so viable and we only keep the good examples, right? So this is the goal of data pruning. Now, I will show you some examples, given that you already had lunch, it's okay. And I will ask you which of these examples would you actually keep in your training and which of them you would throw away. So the ground truth for this one is carbonara, and the model, if you have a model that you do a forward pass of this example, it will tell you carbonara with 53% probability. You have a breakfast burrito, the model thinks it's Greek salad. A hamburger, the model thinks it's steak. Actually what I want to bring up is that sometimes these data sets are noisy, right? So in the data set, the label for this one is carrot cake. Keep this in mind because it happens all the time in real world data sets. In the interest of time, I cannot do polling, so we will continue. So we introduce here essentially a new problem which we call incremental data selection. And what this means is that you are gradually receiving data from a stream, and you have to decide for each example whether you will keep it or not keep it. And if you keep it, then after you accumulate a batch of new examples, you do one update of your model. And of course, the process completes when you have a pre-specified number of examples, let's say K. So in order to do that, of course, you need some initial data set to do a little bit of pre-training, but after that point, the model works in this online incremental data selection process. There is some strong connection between what we do and neuroscience. Unfortunately, within 5 minutes, I cannot talk about that. But we can talk about it in the break. Now, how do we choose basically the good examples from the bad examples? So the idea is that, as I said, you already have a model that is being trained in an incremental way. And when I give you a candidate example, let's say XP, you do a forward pass, right? So you know the activations at the output layer. And you also have some validation examples for each class, right? So these are the examples that you know they're good and true. And what you're trying to do here is you want to ask the question, if I keep this example XP, the candidate example, and I train my model based on that, how will it affect essentially the output of the model for the validation example, right? So that's the question that we ask. And we have a figure of merit here for its example XP. We're basically saying how good this example is. It has to do with how much it will increase the activation of the correct output, which is for that particular XP, you know, some class YV, and how much it will decrease the incorrect activation. So we want to basically maximize this difference. Now, we do a little bit of math there using the neural tangent kernel, and we saw this very simple formula that basically the figure of merit can be expressed as a product of two things. One is the prediction error, which you get after the candidate example goes through the forward pass. So this tells you how big is the error with that example. The second term with the phi's is essentially a dot product between the similarity, the embeddings at the last layer between the candidate example and the validation example for the same class. Now, let me explain this with just a visual illustration. Imagine that the triangles are cats and the circles are dogs, and you have a decision boundary at some point in your model. And imagine that that star is some kind of centroid of all the cats, all the circles, right? And I give you these three examples, one green and two yellow, right? Based on this formula, that you saw over there, you have to choose only the green example and throw away the yellow examples. Why? Because the green example essentially has both a high prediction error and it's close to that centroid of the cats, right? While the example at the top is basically an example that would not help you. It's already correct, right? It has a low prediction error. While the example, the yellow at the bottom, is basically a bad example because it's an outlier. It's very far from the centroid. I think I'm running out of time. Basically, we have, of course, various results that show that the method is very good, much better than random selection, and it competes with, or it's better than the several baselines. So I want to thank you. And yeah, thank you very much.